about question number 1. So in the question number 1, right, the question was asking for which one of them is going to have a strongest interaction with a water molecule. We all know that water is a polar, right, molecule, because hydrogens, oxygens, with a 2 lone pair right there, right, water has a directional being like this. This side is slightly negative, this side is slightly positive. So to have a really strong reaction with it is you have to think about Coulomb law. I don't know if you guys still remember Coulomb law. Coulomb law said that the interaction, the attraction, right, the forces is going to be K, Q1, Q2 over the R squared, radius or distance, right, of the 2 atoms from the nucleus to the nucleus. So pretty much, since on that one, you got to look at your charges, okay? Yes?
Is this K related to the reaction constant?
No, this is another constant. Yes, they keep using K as a different constant, so this is just a constant. You can write C if you want. All right, so you can see that out of there, I'm going to eliminate Na and I'm going to eliminate K because they are the +1 charges. Then you got to compare the two, Mg and Ca, okay? Based on this, the bigger charge, the better, or and the less distance, the smaller the distance, so therefore Mg is the clear winner. All right, let's talk about number 2. Least soluble in water. We just said that water is a polar, so least soluble must be non-polar. We're looking for non-polar substance. Okay, clear things to see. Polarity is a symmetry, or you can say if you see the lone pair and it's not symmetrical, it is polar. So you can see that this is definitely polar. That's a bent shape. This is also polar. That's a bent also. Okay, this is polar, another bent shape. This is not polar. That's a tetrahedral, and then all 4 has the same atoms, right? Okay, make sense? Number 3, let's take a look. One reason that could explain why silver chloride, AgCl, is insoluble in water. So we're looking for insoluble. That means not gonna be soluble. That means AgCl doesn't want to split into 2 things, Ag plus and Cl minus. So what are you guys thinking? C, right? Because they didn't want to split. That means the ionic bond must be very strong. They're holding on to each other for their strongest, right? So therefore they didn't split. Remember, if you dissolve, right, salt dissolve, if the salt is gonna dissolve in H2O, what's gonna happen is this, right? Salt is gonna start with, let's say, NaCl, for example. The moment you dissolve, we're gonna get Na plus and then Cl minus, right? In order for this to happen, what must happen? The iron, the interaction, the lattice energy, that has to be broken. That's why they are far apart from each other and are surrounded by water molecule, right? Ionic bonds. All right, let's talk about the next one, number 4. What's going on with the number 4? All right. The structure is toluene. You see it here. It has rather low solubility in water. What that signal? What do you think? It's probably not as polar, right? Probably non-polar or maybe not as polar, even if it's polar. Okay. Which of the following best describe the intermolecular force interaction between toluene and water? Okay, we're gonna say D, yes, Landon dispersion force, because we're looking for interaction. Okay, it does say low solubility, so no attractive force would be wrong. Okay, make sense? And it can be H bond. If you're hydrogen bonding that is very, very strong, it's gonna be dissolved, right? Iron dipole, that's gonna be also very soluble. Also, beside iron dipole, only happen between what? When do you see iron dipole? Ionic salts. When the salt is dissolved in the water. Okay, we know that this is not salt, so therefore this can't be either. Make sense? So not iron dipoles, Okay, it is sort of look like non-polar, but let's just say we don't know yet. It could be slightly polar because it does dissolve a little bit, but the clear round is because of the no attractive force that make it round, and we know that hydrogen bond meaning very very soluble, when not low soluble, so therefore it's round, right? And then this one make it round. So notice that when you're reading, sometimes it's a key phrase are the one that make this whole sentence round, that you don't have to consider it. You're like, it's not right. Okay, let's look at number 5. What do you guys think? Yep, it is a C. So take a look what happening with a C. It is endothermic, and then we said the last step is exothermic. Well, let's see what happening. Okay, step number 1. You go from the which is close ordered stuff to the far away apart. You need to input energy so that they kind of scatter, right? So that it makes sense that step 1 is endothermic. Step 2, the same thing. They are together to kind of like split apart. That is kind of like endothermic also, right? Because you need to send energy so that for that to happen. Okay. Now, when you talk about C, with C is in this case is exothermic because, right, you can see that everything kind of have their own how to say solute and solvents. They are like dissolving each other, hydration, and we said, let me see, they also say something else in here. Expand, dissolve, ion will be occupied. Ion is inserted into space, shaped by a polar molecule, which is a little bit most stable. Also, kind of makes sense from think about, like, I like it how we have question earlier for solid, liquid, gas, right? So from the like least stable to the most stable, when you're going, you are actually gonna to release energy, so to speak. So in this case, this is the exothermic step, right? Endo, and an exothermic step. Let's see, number 6. Okay, what are we looking at? Greater solubility in water. Most polar.
D.
is out.
Yeah, D is out. Why?
Full symmetrical.
It's definitely totally symmetrical. It's non-polar. So is C. C is also out, right? CH bond, a bunch of CH bond are non-polar. We call them as because carbon and hydrogen's electronegativity difference between them is really small. So if you have just hydrogen and carbons, we can consider them to be non-polar. Okay, hydrocarbons non-polar. Now, A and B are both polar in a sense that they have that OH group, alcohol groups. But which one is most polar? B. A. Because remember, B has a long chain of hydrocarbons followed by the OH, right? I'm not gonna draw all the carbon hydrogen. If you want to see the actual picture, look at Kevin. He actually has the whole thing draw out. Yeah, I'm not gonna draw out. Pretty much remember, this part is non-polar. Only this part is a polar. Okay, kind of. Okay, what this kind of look like is the water. I mean not water. Sorry, the fat like lipid basically. You guys learn it in biology. Maybe some of you guys haven't. Some of you guys see it in a middle school, right? Hydrophobic layer, hydrophilic layer, right? The phospholipid head and then the tail, right? If you look at the structure, the tail is mostly made out of carbon and hydrogen, which is non-polar, and then the head, which has the OH group, that's gonna be a polar. That's where we're getting into. Actually, they have phosphate group. That make it polar. All right, let's look at number 7. What do we get? Oh, all right. Let's take a look. Okay. When a gas dissolves in the water, the process is normally exothermic. Which of the following statement best supports this fact? Okay. Gas dissolve. So that means from the gas you're gonna have aqueous, right? You're gonna be inside the water. Okay. So let's see. All right. You got A and C. So I'm gonna eliminate B and D. We all know why B and D are around. Okay. So let's talk about A and C then. Solubility of gas in the water tend to increase as temperature increase. Okay, this kind of going borderline of thermodynamic. You might have to think about that for a slightly bit. That will tell you what happening. So remember, in a thermodynamic, you have this equation. Yeah, Gauss equation. Okay, so remember at which condition when temperature is increasing, this G is becoming smaller, like negative. Okay. Do you remember what that delta H sign was?
Negative.
It was positive case. Remember? Delta H is positive, delta S is positive. So therefore, when you multiply with it, T is negative, will make this part negative, right? So when you're looking at it, the bigger the T, the more negative it's gonna get, or the delta G is decreasing, right? So if the temperature increasing is gonna make this process happen more, chances are it is the endothermic reaction, right? So endothermic reaction increase in T will make reaction happen more, right? Reaction happen more likely, right? More likely to be dissolved, stuff like that. So that's where it's gonna come in. Now, other things, I don't know if you guys been experienced this before, okay? Gas dissolving water. We had that in December. You guys, yeah, soda. Okay. This soda still dissolved inside better at the hot temperature or low temperature, right? That's why you have the empty can of, you open it and you drink it, you didn't finish, you fridge them. Because if you leave them in the living room, they go flat very quickly. Because it's not quite soluble when you are putting it in the high temperature. Okay, so A would be wrong. Let's talk about C. C says separation of solute particle from each other require a little or no energy, which is true. In that case, that's why it was the highly exothermic process to make this gas dissolve in the water because, because if you need energy to separate solute particle from each other, it would be endothermic process, right? Because you need to input energy to separate the solute particle. You don't. All right, let's look at number 8. Yeah, C. Number 8, what do we get? B? Yes? C? D. Let's go over it. All right. Okay. Let's talk about it again. What is O2? Gas. So we're still talking about it. Gas dissolving water. Okay. If you guys haven't known it yet, let's write it down. Gas dissolve in water increase. Okay, dissolving of gas in water increase as which one increase? Temperature decrease. Okay. But since we are dissolving gas into the water, okay, what must happen to the pressure? Let's think about the pressure for a second. Pressure go up because gas are like floating around. If you want it in a liquid, you kind of force it in, push them in, right? So that's how I like to imagine it. Pressure must increase. Okay. Another way. Have you guys ever seen like those soda cans? They said that do not put it in a hot car. Soda can.
What?
You don't put the closed soda can, closed one, the soda can, put it in a car in the summer. It does explode. Okay. Why? Because gases trying to escape. Yes, it's actually happened in my sister's car recently. She picked up, she have a soda can. She didn't know that the weather was that hot. She put it in a trunk. Right, her trunk was a mess right now because they exploded in that. It was interesting, but
Like
yes.
violently or just like
This has never happened. It'll worse.
Well, I mean, I wasn't there to watch it, so
I'm guessing it's like a water balloon.
probably just a regular. Now, some of you guys might argue you can't put the soda can in the freezer either because it's also explode the other way around.
It's made of water. Water expands when it freezes.
Yes. Do you see that? That's why soda can explode it either way. You can't put it in a freezer because water will expand when it's cold. That's
No, I just put it this
okay.
morning.
Shh. For a little bit, for a long time. Okay. I know that for the fact that those water can, if you put it in a freezer, yeah, you will never get back to the normal shape because it will puff up from the bottom. And if they can't, they will crack open your bottle. It happened to me with those shaker bottles.
wait.
Okay.
So if you freeze it, technically it doesn't make a mess though.
Well, it doesn't make a mess, but your bottle is broke now because it's cracking your bottle open. Right now, if you heat it up, like I said, they will explode. This is also why, if you ever take a look at it, anything pressurized, like I mean, they also have the fire hazard part, but then
Generating high temperatures.
anything pressurized, they said do not put it in a high temperature because they will explode because there's gas in there, right? All right, let's talk about number 9.
That's why I hate shit.
Okay, what's going on with number 9? What do we get? Okay, I have A, I have B. Okay, let's go through that. Okay, which of the following will most likely increase the rate of reaction presented above? Take a look at the rate of reaction. Okay, take a look at it. What's happening? What kind of reaction is this? Yeah, delta S is going down. Delta S is negative because you have 2 moles to 1 mole. Okay, what do you think? So, based off of this, let's talk about it. Because your delta S is negative, okay, which one of these most likely will increase the rate of reaction represented above? Okay, most likely. We're increasing the rate of reaction. Okay. Entropy is going down. Probably the temperature could do the trick. Keep reading the whole thing. What did B say? Okay. Anyone know this? What did catalyst do?
What do you mean by a heterogeneous catalyst?
That means different states. So in this case, see how like these are gas? That means your catalyst is either a solid or liquid. Yeah. Okay. Yes. Good question. Heterogeneous just mean like different state. Okay. This just means different state. Not really. C said increasing the volume of reaction vessel using the pistons. D said removing H2. Okay, I can tell you both C and D are a bad idea because they actually gonna to go the reaction the other way or decrease the rate of reaction. Because think about it. If my volume is getting bigger, what happens to the concentration of the reactant? Go down. Bad idea. And if you remove in the reactant, again, the rate is not gonna go faster, it's gonna go slower. Right? So you end up with A and B. And even though like A is like kind of seem like the right answer, trust me, we're gonna go with the B. Okay. Also for the A, decreasing the temperature usually is associating with whether the reaction is gonna happen on the either direction, so to speak. But the rate, in generally speaking, do faster at the higher temperature. Okay. Remember, because the T, what we're calculating, has to do with associated with the thermodynamic. And then in the kinetic, if you guys remember when we talk about it, temperature increase, that means the rate is increasing. Okay, so which side favor, that's a different question. Now, be careful to not mess up your thermodynamic and kinetic because temperature means different thing. Okay, so technically, this will also decrease the reaction rate. Okay, let's go with number 10. What do we get? Wait, you guys say D or B? B. Okay, good. I was like, D, go back to learning that again. All right, we all get B? Okay. All right. Got it? We were able to figure out? Okay. Can I explain it? Yeah. Okay. So, we want to know increasing reaction rate. We just talked about it. Which one is going to increase the rate of reaction? There's a couple of things that you have to consider. Temperature. Increasing temperature is increasing the rate of reaction, right? Concentration of reactant. Concentration of reactant increase or decrease? Increase, okay? Is powder better or the whole strip of the metal is better? Powder. Okay. So therefore, let's figure out. We said that 2 would be the least, 3 would be the highest. Let's see why is this so. Take a look. Okay. In the 2, do you see that how is that strip? Again, the 4 is also strip. Do you see that? The strip of metal are bad. Look at the temperature. They have temperature the same, but concentration. Okay. 4 has a better concentration. Therefore, 4 is a little bit better, faster than 2. Okay. Now, let's compare 4 with 1 and 3. Let's just say 4 compared with 3. 3 is powder, okay, and also higher temperature. So 3 is better, okay. Now 4 compared with 1, powder, same temperature, but it's powder. So therefore 1 is faster than 4. Do you see that? So that's how you're gonna arrange it. If you can't tell, you can do 2 at a time and then group them together, okay. Or sometimes you just check the middle and you just kind of like, okay, let's just go from there. Okay. Number 11, we'll talk about that later, but.
So say they give us 2 experiments. One with the strip, but the strip is a higher temperature than the powder.
They won't do that because it's harder to tell. Yes, because they will do something like that, then you should be able to compare enough to tell. Yeah, they want to give you 2 that are like opposite, right? Because it's harder to tell. We'll talk about that later. Okay, so yes, we'll talk about that. For now, later, let's talk about number 12. Okay, you sure should know how to do that one. No? It is D. Alright, let's talk about what happened. Rate law. Take a look at this. Okay? In try 2, which reactant will be consumed more rapidly and why? Okay? We're just looking at these 2. Which one is going to get used up or used at the faster rate, so to speak? Take a look at this one. What is this telling you? Look at your balance equation. What is it telling you? 2y for every x. So that means y is disappearing at the faster rate than the x. Make sense? Coefficients right there. Okay, now if you guys want to solve for it, you can also do this way. Take a look. You can also say this. Rate is equal to change in concentration of x over change in time, which is equal to, guys, hold on, 2 times delta t, like that. Okay? But in this case, they are asking you to compare this and this. They're not talking about that too. So delta x rate of disappearing on y is 2 times of that, or this is half of that. Do you see that? So y is disappearing faster. All right. In fact, notice you don't need this table at all. Extra information. All right. Look at 13. What do we get? C. Yes, C is the right answer. Okay. First order. Why? How do we know this? Take a look at this thing. Okay, guys, hold on. Take a look at this thing. Okay. Notice that it is not going straight forward. It's not going straight forward. Differences. right? So then what you have to do is you have to check whether it is ln of H2O2 or 1 over of H2O2 is going to make a straight line when you graph it. Okay. Now you might say, do we need to graph it? No, you don't need to graph it. You can tell from the answer. Now, most than likely, this is not gonna be this is not gonna be multiple choice question. If it's gonna be multiple choice question, more than likely, I will also give you this tables, and then you have to figure out because yeah, I wouldn't make you do the ln of 2.7. Okay, just not gonna happen. Make sense? Yeah, plus also you can also use the process of elimination for this because C is the only one that makes sense. Because remember, order cannot be determined from the overall balance equation. Now, they can determine it for equation if they happen to say this is the elementary step. Okay? There's nothing on that say elementary step. So you cannot say that this is a second order. Now, if you know if it's elementary step, you can say this is a second order. You can use this as a coefficient as a power. Okay? So therefore, we can say that. And then so that means my A is out, my B is out. Okay? My C and D, you know there's a first order is a ln. First order is not 1 over. 1 over is a second order. Okay? That would be this. Okay? Alrighty. 14. What do we get? We all get B? Okay. How do we know B? Activation energy. That thing. Okay? Activation energy is what is changing the rate of the reaction, and catalase is the one that is decreasing the activation energy, therefore increasing the rate of reaction. Okay? 15. What about 15? B. Good. Well, got it? It's a fast order. Again, see how I said it? I will give you a table that you should be able to tell. Pressure, yes, this time they give you pressure instead of mole, but it's the same thing. Pressure and mole has a direct relationship. You can use them to tell. Okay. In the gas case, they will give you pressure sometimes instead of mole. 14, B. Because the bumps here, right? This bump is bigger, so therefore higher activation energy, slower reaction. Okay.
Wait, so 14, 15B.
Okay, guys, pay attention. I'm not gonna go back again. Let's look at number 16.
I hope it's C.
You hope it's C, and that might be A. Okay, let's see.
C.
All right, let's first start with it. What I don't need to know the actual number. Let's just start with the unit first. What kind of reaction that we said that 15 was? First order, right? So first order is gonna be rate is equal to what? K time concentration, right? That's the first order. Yes? All right. So in this case, you can't do that way because the way that it was given is slightly different. They give you the ln version, and then they don't have the time thing. So I mean, they have a time thing, they don't have a rate thing. So what you're gonna do is you're gonna use the linear equation, integrated equation. So what is this? Integrated equation is ln. Okay. Again, you can use this instead of concentration. So I just say P N2O5 over T is equal to K time negative. Yep. KT plus ln of P N2O5 at the time 0. Okay. And we do have a time zeros. Huh? Oh, because this is not concentration, this is the pressure. So that's why I use a parenthesis instead of bracket. Yes. Now, if you want to use a bracket, you can. But yeah, I'm not using that one for this case. Okay, so we do have a time 0 and we do have a time 100. You can write it down. Now notice that what they give you here is ln. So you do not need to ln it again. Got it? So this is 4.3 is equal to negative k. My t is 100 plus 5. Send it over. That's the easy part of the math. Yes? We all should know how to do that math.
No.
Negative 0.7.
Negative 0.7, okay, equal to negative k. Oh no, 0.7 over 100. Forgot to divide it by 100. Okay? So that will be a positive k. You will see I need to move the decimal places. 0.007. Okay? 0.007. Okay? Now, notice that 0.007 had two of them. Okay? Well, now you have to think about it. Rate is equal to k time of the concentration. You can say concentration. I don't want to say that. So what would that k unit should be? Per minute only. Okay. You don't need the ATM per minute, stuff like that. Okay. Now you can use, if it's second order or something, yes, you will have the ATM per ATM minute. All right. 16, 17. Okay. Which of the following is the first elementary step or the two-step if the first step is slow and the second step is fast? Notice that you have a rate equation. That should give you a hint of which one is your slow step, elementary step. Okay. So what did I mean about these two? These two are going to be reactant of the elementary step. So take a look at it. Which one has these two as a reactant and a coefficient of 1 because their power is 1. Okay, B. Make sense? Okay, that's all we're doing. Yeah? You guys do a lot of work for nothing?
No, we did some
You guys just... Alright. Make sense? That's how I'm looking at it. Okay, 18. Could be long, but could be short too. Let's take a look. All right, reaction mechanisms and the rate law. Okay, we have a rate law here. Reaction mechanism. Take a look at the slow one. Slow, slow. Did these two matches this? Yes, because remember, that tell you that it's a first order. This tell you it's first order. This is a first order rate law. It matched. See that? Both mechanisms, 1 and 2, are consistent with the rate law. I don't need to check for the rest. I'm just checking that one. Got it? The second one would be second order why? Because you're checking the slows elementary step, and then when you check the slow elementary step, all you see for reactant was X2. There's only one of them. First order. So let's say like if this one were the slow order, then you're gonna say this time K is equal to rate. But this is not slow, this is fast. Okay? So whatever one is slow. See? For example, if this were the elementary step, then it's gonna to be this square times this times K. But this is not elementary, this is overall. So you have to find the elementary. Okay? Alright, 18 is C. 2 more. 19, 20, and 3 more. 19. Oh, that's a harder one to do. Is D. Now, notice why this one doesn't quite match. Because you have a first reversible equation and your N2O2 is your intermediate. Remember this one? This is intermediate. When you write down the thing, you don't use intermediate as your rate law. So you have to figure out how to write it. So remember in class, we did it before. I want to do one more time. Let's call this top 1 and then let's call this bottom 2, just because. And then let's say this is 3. Okay? So good so far? Okay, I'm going to write the rate law for each one. So for 1, it's going to look like this. Rate is equal to K time NO square. Let's just say K1. Okay. Make sense? And then the other direction is rate is equal to, so I'm doing 1, 2, and then 3. K2, let's say N2O2. The third direction is rate is equal to K3, let's say N2O2, O2. Okay, see that? Okay. 1 and 2 is pretty much the same rate law, right? Because you're going forward and reverse, kind of, basically. So what you're gonna do is you're gonna set this up to be the same thing. So you're gonna say these two are same because come from the same thing. So we're gonna say K N O square is equal to K2 N2 O2. Okay. Make sense? That's what we're getting at. Now notice that I need to replace the N2O2. So N2O2 is gonna be K over K NO squared. That's gonna go to here. So you already have K3 and you're gonna have K over K and then you're gonna say NO squared and then O2. Okay. Notice that all the K, I don't care is 1, 2, or 3. They are all basically called together as K. Right? Because they're all constants anyway. So therefore your answer is K NO squared and then O2. Do you see the rate law? You found the answer? Yeah, that would be a D. Or, like he said, you can eliminate everything else. Let's take a look. Can we eliminate everything else? Take a look at number 1. Step 1 represent unimodal reaction. No, there is 2 of them, so it's not correct. It should say dimolecule. Right? Make sense? 2 said increasing concentration of NO will decrease the overall rate of reaction. No, it should increase the overall. Because take a look. More NO meaning more N2O2. More N2O2 meaning more of the NO2. Overall reaction should be faster when you're increasing the reactant. Not decrease, that make this thing wrong. Okay? C, increase in temperature have no effect. Trust me, we talked about it before. Remember this graph? The temperature and the K, as the temperature increase, what happened in the K? K increases. That's something like that. Okay? Alright, number 20. What do we get? A should be B. Okay? Because collision theory, you guys have to remember collision theory. That's what make it happen. Okay? 21, what do we get? D. Okay? That's why it's shorter.